Imagine you're driving down the highway and a massive truck is cruising alongside you at the same speed. You glance at its wheels and something looks wrong. One of the middle axles isn't touching the road at all. The tires are spinning freely in midair with a visible gap between the rubber and the asphalt. Your first reaction is obvious. Something's broken. The suspension failed. The frame must be twisted. But don't rush to honk or flash your lights. What you're seeing isn't a malfunction. It's the result of engineering decisions worth hundreds of thousands of dollars. There is, however, a darker side to this system. When used incorrectly, it can seriously compromise braking performance and vehicle stability. In professional circles, it's sometimes called a silent problem because everything looks normal right up until the moment it isn't. Engineers call this system a lift axle, often nicknamed the lazy axle. It's both a brilliant cost-saving tool and a potential hazard if used outside its intended limits. The road surface only appears rigid. Under the weight of a heavy truck, asphalt behaves very differently, especially in summer, when pavement temperatures are high and axle loads approach legal limits. That's why road regulations don't focus solely on total vehicle weight, but on how that weight is distributed across individual axles. Imagine placing a heavy cabinet on freshly laid asphalt on a hot day. If all the weight rests on just a few narrow legs, the surface deforms and sinks under the pressure. But if you place the same cabinet on wide supports that spread the load, the asphalt holds its shape. A lift axle works on the same principle. It reduces pressure by increasing the contact area. When a truck is empty, 2 or 3 axles are enough. But load it with 20 tons of gravel, and the pressure under the main wheels becomes critical. The asphalt begins to deform, forming ruts. Lowering the lift axle instantly increases the contact area. The load spreads out, the road stays intact, and the truck remains legal. There are several configurations. A pusher axle is mounted ahead of the drive axles and is more common in North America. A tag axle sits behind the drive wheels and is typical of European trucks. The choice depends on vehicle layout, legal axle limits, and the truck's intended use. The system operates through air suspension. Pneumatic components inside the frame redistribute pressure between axles. When the driver activates the lift function, part of the load is relieved, and a dedicated lifting element pulls the axle up toward the frame. The entire process takes only seconds, but the truck's behavior changes dramatically. In freight logistics, one of the biggest enemies of profit is rolling resistance. Every tire in contact with the road consumes energy. Even perfectly inflated tires constantly deform under load, heat up, and steal power from the engine. On short trips, this is barely noticeable, but over hundreds of thousands of kilometers per year, those losses become real money. When a truck runs empty or lightly loaded, an extra axle becomes unnecessary resistance. In that state, it truly acts like an energy parasite. Lifting the axle brings several tangible benefits. The first is fuel savings. Reducing rolling resistance cuts fuel consumption by roughly 5 to 10%, depending on configuration and driving conditions. For a tractor covering around 200,000 kilometers per year, that translates into thousands of dollars saved, without changing the engine, route, or driving style. The second benefit is tire life. Heavy-duty truck tires are expensive, and every additional axle accelerates wear. When the lift axle is raised, its tires are no longer in contact with the road. That directly extends the service life of the entire tire set and significantly reduces fleet operating costs. The third advantage is maneuverability. In turns, multi-axle trucks suffer from lateral scrub. The rear wheels don't roll freely, but slide sideways across the asphalt, grinding away the tread. Raising the axle shortens the wheelbase, reduces resistance in corners, and makes the truck noticeably easier to control, especially in urban environments and tight yards. In some cases, savings also appear on toll roads, where fees depend on the number of axles touching the pavement. However, modern WIM, weigh-in-motion, systems measure axle loads while the vehicle is moving. Driving fully loaded with a lifted axle is easily detected and usually results in a fine that wipes out any financial gain. The braking paradox: why the lazy axle becomes dangerous. The real danger appears when a lift axle is used incorrectly on a loaded truck, especially during braking. Modern trucks are equipped with EBS, electronic braking systems, that adjust braking force based on axle load. Pressure sensors in the air suspension send data to the control unit, and the system distributes brake pressure correctly according to its algorithms. When a fully loaded truck raises an auxiliary axle, the entire vehicle mass is transferred onto the remaining axles. Air pressure in their suspension rises sharply, and the system commands maximum braking force. From a software perspective, everything is working as intended. The problem is physics. Brake systems are designed to dissipate energy, assuming a certain number of active axles. When fewer axles are in contact with the road, the same kinetic energy is converted into heat over a much smaller braking surface. Brake discs and pads overheat within seconds. Brake fade sets in. The friction coefficient drops and stopping distance increases dramatically. At that point, the driver can press the pedal as hard as possible, yet the heavy vehicle continues forward with little deceleration. This is why a lifted axle on a loaded truck turns it into a potentially dangerous machine. There is, however, a situation where load redistribution is used deliberately and correctly. This mode is called traction help. On an icy or slippery incline, an empty or lightly loaded truck may lack traction on the drive wheels. In this case, the system partially reduces pressure in the air springs of the auxiliary axle, shifting more weight onto the drive axle and improving grip. Crucially, the axle is not fully lifted. The mode is designed for low speeds and short durations only. During operation, loads on the drivetrain, differential, and frame rise and approach their upper design limits. If the driver forgets to deactivate traction help after returning to normal road conditions, accelerated wear, or even structural damage can occur. Anatomy of the lazy axle. What this module is made of. If you look underneath the chassis, a lift axle turns out to be far more than a spare beam. It is a fully engineered subsystem where every component affects stability, durability, and safety. The first critical element is the hub and unsprung mass. Engineers constantly balance strength against weight. The wheel assembly must be light enough to maintain road contact over uneven surfaces, yet strong enough to withstand sudden dynamic loads when a raised axle is lowered at speed or briefly contacts the pavement. The second major issue is brake corrosion and seizure. When the axle is lifted, its brakes are inactive. They do not heat up or self-clean. Moisture, road salt, and dirt accumulate on the discs and calipers without being burned off during braking. As a result, brake components on lift axles tend to fail significantly more often than those on permanently loaded axles unless they receive regular maintenance. The third and most important element is pneumatic logic. The main air springs push the axle down onto the road. Lifting the axle requires a separate lifting bellows. When the system releases pressure from the load-bearing air springs, this lifting bellows contracts and pulls the axle beam up toward the frame. The entire operation takes only a few seconds, yet it completely changes how loads are distributed across the chassis. The era of automation in Volvo dynamic tag axle. Manual control of lift axles is gradually becoming obsolete. Modern tractors from Volvo, Scania, and Mercedes are equipped with load sensors that continuously monitor suspension deflection. Changes in vehicle weight are detected automatically, and the system decides on its own when the axle should be raised or lowered. The next step is active axles. The Volvo dynamic tag axle transforms a passive auxiliary axle into a steerable one. At low speeds, its wheels turn in the opposite direction of the front wheels, reducing the turning radius and almost completely eliminating lateral scrub. This is especially valuable during tight maneuvers in cities and crowded terminals. Looking ahead to electric trucks, lift axles become even more important. A raised axle reduces rolling resistance and energy losses. In a world where every kilometer of driving range matters, such solutions directly affect real-world autonomy and operating economics. Wheels spinning in midair are neither a malfunction nor an illusion. They are the result of precise engineering, where economics, environmental concerns, and mechanical laws intersect. Understanding that balance is what separates professional operation from dangerous compromise.